Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So I think we have a few questions left over from last time. I see one here from Amarita. The question was, do protons decay? Okay, interesting question. We don't know the answer for sure yet. Nobody has yet seen a proton decay. What would it mean? First of all, what does it mean for a proton to decay? It means that if you had a proton, that it would simply spontaneously turn into a collection of other particles. So you say, does that happen for any of the particles we ordinarily know? Well, it does happen for neutrons. So atomic nuclei consist of clumps of protons and neutrons all stuck together by the strong nuclear force. And so, for example, helium, for instance, the most common version of helium has 2 protons and 2 neutrons in its nucleus. That's helium-4. The 4 means a total of 4 protons and neutrons. So helium-4 is stable. The 2 neutrons that are in the nucleus of helium-4 are perfectly stable, as are the protons. But if you were to separate a neutron out and you had a free neutron, it turns out that free neutrons left on their own, not bound into atomic nuclei, actually decay in about 15 minutes. So what happens in the neutron decays into a proton, an electron, and in fact an antineutrino. So to figure out what something can decay into, you have to work out what things it has to conserve and what things it does not conserve. So in the case of one of the things that seems to be a thing that gets conserved in the universe is electric charge. So you can't create or destroy electric charge. So a neutron is electrically neutral. And so if it's going to decay into something, it has to decay into things where the total of what it decays into is also electrically neutral. So protons have an electric charge of +1 unit. Electrons have an electric charge of -1 unit. Neutrinos have no electric charge. So a neutron, to say it decays into a proton, an electron, and an antineutrino, that works in terms of conserving electric charge, because the proton is +1 minus the electron is -1, the neutrino doesn't contribute anything. The next big question is when it decays, it will have a certain mass. And if it's going to decay into other things, the total mass of the things it decays into must be less than the mass it has itself. Because otherwise, it's not possible for it to just sort of create mass from nothing. So when a neutron decays into a proton, electron, and antineutrino, it so happens that the mass of a neutron is just a little bit higher than the mass of a proton plus the mass of an electron. So neutron mass is a little bit higher than the sum of the masses of proton, electron, and the antineutrino has almost 0 mass. So it's because the mass of the neutron is a little bit higher than that sum of those masses that it can decay into a proton, electron, antineutrino. Now, it turns out when a neutron is inside a nucleus like helium-4, it is bound inside the nucleus strongly enough that effectively its mass is reduced by enough that prevent the possibility of it decaying in the way that I just described. So a free neutron, which isn't bound inside a nucleus, can decay in 15 minutes or so, but bound inside a nucleus, it usually doesn't bound inside, where it's tightly bound inside a nucleus, like it is in the case of helium-4, it can't decay. Okay, so what about protons? If a proton was to decay, what would it decay into? Well, it has to conserve charge. So that means it should be decaying into a positively charged particle. What positively charged particle is lighter than a proton? So the only answer that we know of to that is a positron, the antiparticle of the electron. So a proton weighs, in the units usually used in these kinds of things, about 938 MeV. MeV stands for mega electron volts. That's just a unit of mass. In kilograms, it would be, I think, 10 to the minus 26 kilograms or so. But it's more convenient to talk about it in terms of MeV. The proton weighs about 938 MeV. The electron is about 1,800 times lighter than a proton. Electrons only weigh about 0.51 MeV. And so that, and positrons have the same mass as electrons. That's a rule for antiparticles always have the same mass. They have the opposite charge, but they have the same mass. So a positron has charge +1, mass 0.5 MeV. And so in terms of just pure energy, in terms of just pure mass, a proton could decay into a positron plus maybe a bunch of neutrinos. Okay, the question is, does it? And what happened around the late 1970s, people developed a bunch of theories, so-called grand unified theories, which said it should be the case that protons can decay in the way that I just said into positrons and so on. And so people went and looked for decays of protons and they didn't find them. So let me describe both why people thought the proton should decay, how they looked for proton decay, and what we know about that so far. So in terms of why protons should decay, okay, here's the basic idea. So it all has to do with these things called gauge theories. And in studying things like protons and neutrons and quarks and photons and electrons and all these kinds of particles that exist, it's the main way to study those is using quantum field theory, and in particular using this idea of gauge fields. Let's see if I can explain how gauge fields work. So essentially the notion is that this is going to be a little tricky. Let's see what I can do here. The simplest example of a gauge field is electromagnetism. The fact that photons exist can be seen as a consequence of this notion of local gauge invariance. All right, let me see if I can explain how this works. So let's say you have an electron. An electron has an electric charge. Electric charge produces an electric field. When there's an electric charges, two unlike charges will attract, like charges will repel. The way we represent that phenomenon is through the presence of this electric field. We imagine that there's this field that exists, that is generated by the electron, but exists outside of the electron, exists everywhere. If another electron is also in this field, there will be a force on that other electron as a result of the field. And the way it works is the field of a single point charge is this thing that looks like a sort of idealized hedgehog. It has all of these kinds of lines of electric field that go out in all directions from that electric charge. Okay, so that means you've got this charge, it's got this electric field, the electric field goes out in all directions. If you try to say, well, where is there an electric charge? Okay, we can see where it is because we can go in any direction. We can go as far away as we want, and we can see, can we detect an electric field that was a consequence of this kind of hedgehog electric field lines that came out of this charge. The intensity of the electric field goes down like an inverse square, like 1 over the distance squared, but nevertheless, there's some electric field even as far away as you might go. Okay, so now let's imagine that we move that electric charge, the one that we have just at the origin. We move it, we just push it a bit. Okay, so eventually it better be the case. So when we move it, it's going to move to a new position and it's got a new set of electric field lines coming out of it. So we go far away from this electric charge. The electric field lines have to have shifted because they're now the electric field lines from a different position of electric charge. The question is, how does that process work? How do the field lines sort of realign themselves with the new position of the electric charge? And the answer is you have to have some kind of, there has to be some front that, you know, you've got this one kind of hedgehog-like shape, you're going to get to another one. There has to be some sort of front that exists. And the first one that kind of goes outwards, kind of sharing the information that, yes, the electric charge in the middle moved. So that front, the existence of that front is electromagnetic radiation. That is the thing that kind of establishes that something like a photon must exist. The fact that you somehow have to convey the information that you moved the charge around, it has to be conveyed. That information has to eventually be conveyed as far away as you choose to look. And that information gets conveyed, as it turns out, at the speed of light, and it gets conveyed by the presence of essentially photons that sort of carry the information that the electric charge moved. So in a sense, whenever there's something like an electric charge that generates this field, and by the way that you convey information about a change of the electric charge is by the presence of particles like photons. So it's sort of an inevitable feature. Once there's this electric field and it works the way that it works, it's inevitable that there must be things like photons that exist that sort of carry information about that field around. Okay, so the thing that what's a little complicated is that when how to explain this? I'll tell you the fancy words that describe it. There's this notion, it's the theory of gauge groups and things called Lie groups, spelled L-I-E, and it has to do with, okay, so when we have ordinary electric charge, it's just a number. It's just, you know, something has charge +1, +2, charge, whatever, it's just a number. There are different kinds of charges that work in a more complicated way. So for example, quarks have a thing called color charge. And the analog of photons for quarks is gluons. Gluons are the particles that kind of carry the information about color, about the color field. Unlike photons, okay, so what happens with color charge is more complicated than happens with ordinary electric charge. With color charge, there isn't just one number that characterizes the color charge of a quark. Color charge kind of comes in three directions. It's kind of like red, green, blue colors. And a quark can have, you can kind of, when a sort of a red quark emits a green anti-red gluon, emits a red anti-green gluon, and then maybe it turns into a green quark. In other words, unlike in the case where there aren't real colors, this is just mathematically talked about in terms of colors. But when an electron emits a photon, it does not change its charge. When a quark emits a gluon, it does change its color charge. And it does it in this kind of, these three directions of color charge that exist. And one of the many complexities is that whereas a photon does not have electric charge, a gluon does have color charge. So photons don't directly interact with each other because they're not attracted by electric charge to each other because they don't have electric charge themselves. Gluons, on the other hand, do have color charge, so they have interactions between themselves. And that creates a lot of complexity in understanding how quarks and gluons work, and is the reason that you can't separate two quarks apart. I mean, if you start pulling quarks apart, there will be gluons that will generate essentially a color field between the quarks. But because these gluons interact with each other, instead of the sort of the field lines going out like a hedgehog, all in different directions, all independent, these gluons interact with each other and they pull essentially the field lines together. So instead of these quarks just having like sort of the fields going out in all directions and having sort of an inverse square law of what the density of these sort of hedgehog lines is, as you go out to a certain distance. Instead of all of that, these gluons interact with each other and they pull the field lines together. So what happens is that instead of these field lines going out in all directions, they're pulled together into this kind of string between the two quarks. So instead of it being the case that as you pull these quarks apart, they are sort of more and more, less and less affected by color forces associated with the other quark, they're affected just as much as you pull them apart. In fact, even more so as you pull them further and further apart, because you get all of this, all of this kind of color field is concentrated in this sort of string between these two quarks. It's not the way that, if you've heard of string theory, it's not the way that modern string theory works. It's the way that a previous iteration of that kind of string theory talked about those kinds of things. But in any case, so that's a case. So quarks are a case where there is the same kind of idea of something like electric charge, electric fields, electromagnetic fields, photons, and so on, but it works a little differently. The official name is it's a so-called non-abelian gauge field. That means that it's a gauge field that interacts with itself as well as interacting with the source of field like the quarks and so on. Okay, long story here, but basically what was found was that in particle physics, there are, you can characterize these different kinds of charges, and there are three different kinds of charges that show up in particle physics: color charges from quarks, electric charges from electromagnetism, and a third kind of charge that's associated with the so-called weak interaction that is the thing that leads to certain kinds of radioactive decay, beta decay, and so on. It's again a little bit complicated because there's a mixing between the electromagnetic force and this weak charge piece, but roughly there are these three separate things: color, weak force, electromagnetism, and they're all characterized by these. They can be written down mathematically in terms of basically saying, in terms of these groups that define. They're basically describing sort of how many directions of how many numbers in effect characterize each kind of charge roughly. And so the official version of the standard model of particle physics, it's a SU3 cross SU2 cross U1. And the SU3, the 3 is the sort of three directions of color charge. The SU2 has to do with weak charges, and the U1 has to do with electromagnetism, and just the scalar, this number that characterizes electric charge. Roughly, that's how it works. I could go into a great deal more detail here. But that's a rough picture of how that works. Okay, so people wondered, how come these different things, the strong interactions, the quark-gluon stuff, the weak stuff, and the electromagnetic stuff, how come they're all separate? Surely there must be some unification of these things. Surely there must be some way to have sort of a sort of global kind of charge that just as special cases has color charge, weak charge, electromagnetic charge. And so what people imagined is that all these things might be combined into, let's say, a 5-direction thing, SU5 or something, that just only special cases of which correspond to strong interactions, weak interactions, electromagnetism. So there was this kind of idea there would be this sort of master version of things that would be would include all of those. Okay, so one consequence of having that master version is it means that there have to be processes that will turn things that are usually associated with the strong forces, the QCD forces, the quark-gluon forces, into things that are usually associated with these weak forces. So in the language of particle physics, these things that are that are made of quarks and gluons and so on are called hadrons, things that interact strongly with each other, things that are subject only to the weak forces or also to electromagnetism are called leptons. That word comes from the Greek leptos, which means light, because those used to be the particles that had lower mass, although now there are heavier leptons that have been found, so that's a little bit confusing. But one of the features of kind of unifying together all these different things is it implies that the quark-like things must be able to be transformed into the electron-lepton-like things by emitting some kind of particle. And that particle would actually be a particle that in effect lives only a very, very short time. But it's nevertheless, and it's something which would happen, that process would happen potentially only very, very, very rarely. And so people tried to work out, well, how often would it happen? And one idea was maybe it happens, maybe the average lifetime of a proton might be 10 to the 30th years. So that means that's 10 to the 30th means a trillion billion, if I got my math roughly right, years. So that's a long time. I mean, our universe is only 15 billion years old. But the way these things work, when you say that something has a lifetime of such and such a number of years, what that actually means, that the most common thing to quote is the so-called half-life. What that means is after, as you say, it has a half-life of a year. Okay, that means when 1 year has gone by, half the examples of that thing will have decayed. When 2 years have gone by, half squared examples will have decayed, and so on. And so it'll be, and so this idea. So what happens is every time there's it halves every time you go another half-life of time forward. So the first year it's halved, and the second year it'll halve again, third year it'll halve again, and so on. So that's the notion of a half-life. And from what we know about quantum mechanics and the way microscopic particles work, things that just freely decay into other things will always decay on this, you halve the amount of, half more of the things will decay during the next period of that half-life. And so the calculation was that the half-life of the proton might be around 10 to the 30th years. So you'd say, how could you possibly detect something which decays only that slowly? Well, the answer is, if you have enough protons, then the chances are that one of them, even if the half-life is 10 to the 30th, that means even in 1 year, some tiny fraction of those protons will decay. It's just it would take you 10 to the 30th years for half the protons in a sample to decay. And so what people did was they were interested in looking for, if you have a giant tank of water, for example, could there be just one proton in a year that in this giant tank of water that might contain, 10 to the 30th protons, for example, might there be one proton in that tank that decays in the whole year? What would it look like if the proton decayed? Well, the proton is going to turn into let's say a positron and some neutrinos. And so what does that actually mean? Well, it means there's a proton, it's sitting there, it's sitting in a tank of water. Maybe it's in one of the hydrogens of the water that you have there. And suddenly it decays. And what will happen when it decays is all the energy associated with the mass of that proton will be turned into kinetic energy, will be turned into the motion of the electron. So there'll be this proton will just be sitting there, and then this electron will whiz out of where the proton was. And to conserve momentum, there'll be some neutrinos that go in the opposite direction, but neutrinos don't interact much, so you probably won't see them. But they'll be basically, what will happen is you'll go from this thing where there was just a quiescent, just a bunch of water there, and then suddenly this positron that has a whole bunch of energy that's taking probably, let's say, half the energy of the mass of the proton, just going to suddenly start zooming through the water. Okay, so how would you detect that? You've got this giant tank of water. How would you detect that just one, proton decayed and produced this high energy positron? Well, boy, I'm having to explain a whole bunch of physics here. Okay, so there is a phenomenon called Cherenkov radiation. This is one of the ways there are a variety of ways you could detect that electron, but one way that's a pretty good way to detect that positron is with this thing called Cherenkov radiation. Let me talk about that in a moment. But in any case, what people tried to do back around 1980 or so was they tried to get giant tanks of things like water, and they tried to see, you just set it somewhere and you try to see, is there suddenly this sort of flash of a decay of a proton? Okay. Now, one of the problems is you just put a tank of water out there in your backyard or whatever, all kinds of weird things will happen to it. For example, one of the things that will happen is there are cosmic rays that come mostly from the sun. Just as we get light from the sun, there's also a stream of protons that come from the sun. And those protons hit the upper atmosphere of the Earth, and they usually interact there. And eventually they produce muons near the surface, and they produce some electrons and other things. But actually, I just got a little detector, which is now connected to my computer, and I have to have a look at it again, but which actually detects cosmic rays as they go through my computer. But every, if you have for us the size we are, so to speak, roughly every minute or so at sea level at least, there'll be a cosmic ray particle that goes through us. So if you have your giant tank of water and it's out in your backyard, every so often there'll be a cosmic ray particle that comes from the sun, typically, that goes through it, and that can produce the same kind of effects as one of these proton decays. So that's a bad thing, because you might say, I got a proton decay, but you'd be wrong, because it would actually be just this cosmic ray particle from the sun. So how do you avoid that? Well, the answer is you put your tank of water really deep down. So there's a giant bunch of rock between where the cosmic rays are coming and where your tank of water is. So people found all these places like deep mines that are several miles below the ground, where people have dug down to mine for gold or mine for other kinds of materials. And so these giant tanks of water were put in deep mines. Another place where there was, I think a proton decay experiment was done, was in the road tunnel in the Mont Blanc in the Alps. In the Mont Blanc, the tallest mountain in the Alps, there's a tunnel, a road tunnel through it. And by the time you've got that great big mountain on top of you, that's a pretty big pile of rock that can shield out the cosmic rays. But anyway, so people looked for proton decay and they didn't find it. And so far as we know, protons are stable. At least we know that their lifetime is, I think, probably more than about 10 to the 32 years. So protons aren't sort of readily decaying. Now, I'm going to give two little sideshows to this. There is some reason to believe that at some point protons must decay, because there are a bunch of explanations. In fact, I was involved in some of these for why there is more matter than antimatter in the universe, that rely on the fact that eventually it must be possible for protons to decay. That's a slightly complicated story to tell. Maybe I'll tell that if people are interested. Just to come back on one other thing I was talking about was Cherenkov radiation. Let me explain that. It's kind of interesting. So if you're a plane flying through the air and you hear the plane, it's got its engines, it's got a lot of turbulence in the airflow around the plane. You're on the ground, you hear the plane. Okay. The speed of sound, the speed at which the sound from the plane gets to you, is faster than your typical average, passenger plane or something flies at. Okay, so here's a weird thing that can happen. Let's say the plane is flying faster than the speed of sound. Question is, what happens to the sound of the plane as it flies through the air? And the answer is that all that sound is kind of concentrated in this sonic boom, which is this kind of cone of effect that the plane has on the air that it's going through. And it's a general thing. If you ride a bicycle through a puddle, you'll see that there's a if you're riding at a reasonable speed, you're riding faster than the speed of waves on the surface of the water. And so you'll see this kind of wake that comes back in a kind of in a triangle behind where you are. That idea of what's happening is, whenever you are going faster than the speed of whatever, let's say it's sound or water waves on the surface of the water, when you have a thing that's going faster than the local speed of that of sort of transmitting information, you get this kind of shock wave. You get this thing that, in the case of sound, is a sonic boom. In the case of water waves, it's kind of this sort of dramatic wake. Okay, so this also happens with light. So the fastest light ordinarily goes at the speed of light, but the speed of light is a certain speed in the vacuum. If there's nothing, if the light is not interacting with anything, but as soon as the light is in is going through something like water, for example, it goes slower than it does in the vacuum. What's happening is the photons are coming into the water. The photons keep on getting absorbed by an atom and then re-emitted by the atom, but there's a slight delay for the re-emission. So in water, the speed of light is about 1.3 times slower than it is in the vacuum. So okay, so that's just a fact. Well, it turns out in the case of something like proton decay, that positron will have been pushed out and it will be going faster than the speed of light in the water. So faster than the 1.3 times slower than the speed of light in a vacuum. So it'll be going close to the speed of light in a vacuum, which is faster than the speed of light in water. And so what happens is that you get the analog of a sonic boom, but now with light instead of with sound. You get this cone of light produced that is the result of the actually I should, if the positron is going that way, the cone comes behind the positron. The cone of light produced by this particle that's going through the water faster than the speed of light in water. And so this produces Cherenkov light. Is usually it's bluish light. Because of the way the spectrum of the light works, it'll appear to be blue light. And so what happens is when this positron is produced, there's a little flash of blue light that is the Cherenkov radiation associated with that thing going through the water. And so people trying to detect proton decay, one of the methods was you just put a lot of essentially cameras, officially photomultiplier tubes, but they're basically cameras, on all sides of this water, and it's completely black. And then suddenly, boop, there's a little flash of light. And that flash of light is the Cherenkov radiation from one of these high energy particles going through the water. Now, so people looked for, did they have these flashes of light from proton decay, and none was ever found. So anyway, that's the long story of proton decay. Maybe I should say something about why we think protons might decay. Boy, I thought this was going to be an easy one to answer. This is what's always interesting about this for me, is that there's a certain sort of map of what there is to know in an area like physics, and there's like, to talk about one thing, how much other stuff do you have to talk about to be able to explain that one thing? All right, let me talk about another sort of interesting piece of sort of physics meets the universe as we live in it. The question is, there's matter like protons and electrons and so on. I think in previous live streams I've talked about antimatter, which has positrons, which are anti-electrons, antiprotons. All these things are the negative charge version, the opposite charge version of ordinary particles. You combine them together, they will just turn into things like photons and so on. They'll essentially just turn into energy. Okay, so one of the things that's really weird is that in our universe, that we didn't end up with an equal amount of matter and antimatter. When I was a kid, it still seemed possible that other galaxies might be made of antimatter, that our galaxy is made of matter, but maybe the Andromeda galaxy, the nearest other spiral galaxy, big galaxy, might be made of antimatter. That seemed like a possible hypothesis. And maybe what would happen is that half the galaxies in the universe might be made of antimatter and half might be made of matter. And one might even imagine all kinds of weird and crazy things, like some galaxies rotate clockwise, others rotate anti-clockwise. Maybe the anti-galaxies are rotating anti-clockwise. Who knows? All kinds of weird things might be true. But it turns out there's pretty good evidence that that's not the way things work. There's pretty good evidence that every galaxy in the universe is a galaxy, not an anti-galaxy. that there's basically matter in the universe, but not any significant amount of antimatter. And so it was hard to understand how that would be the case, because a lot of theories about how the universe started will have meant that there will be an equal amount of matter and antimatter produced. And you have to kind of explain why it didn't stay that way. And the main way of explaining that has to do with the fact that the antimatter, in some sense, decays away. And the way that that decay process works has to be the same kinds of processes as would cause proton decay in the current universe. So in that explanation of why there's more matter than antimatter, it has to be the case that there is some process by which protons do decay, and that process will have happened very, very quickly at the beginning of the universe. Now it will be a really slow process to do with protons just really slowly decaying. But we haven't seen this, and so we don't really know that that's correct. But that's the current theory for why there's sort of more matter than antimatter, and I'm not going into the technical details of how that works. So happened I was involved in working out that theory back around 1980. So if my memory is still working, I could probably tell you in great detail how the theory works. It actually involves some fairly elaborate physics. That's sort of a mixture of the physics of large-scale cosmology and large-scale features of gravity, together with the physics of statistical mechanics of things where there are a large number of elements, large number of particles in a system and how that works, together with particle physics, together with quantum field theory. It's actually a fairly complicated collection of different areas of physics that have to come together to explain this why there's more matter than antimatter in the universe, but maybe for another time. All right, let's go down some more of these. Okay, there's a question from Ollie here. Theoretically, if there was a ladder stretching from Earth to a distant planet, say a light year away, could you communicate with folks there instantly by pushing and pulling the ladder, say in Morse code style? Interesting question. Okay. So the basic problem is, let's say you have this ladder, say you have this pole, and it was a whole light year long, or 4 light years long. So it was reached all the way from here to the nearest star, nearest star other than the sun, Alpha Centauri. Okay, you say that's a very, very long pole. But now let's say we push on the end of the pole. So our usual experience is, if we have a solid object, we push one end of the solid object, and the other end of the solid object will move instantaneously. It's like we just have this pole. So great, we just push it, and the other end will move. Okay. Well, it doesn't really quite work that way. What's happening is that pole is ultimately made of atoms, and the atoms have forces that keep them set up in this kind of solid structure that they're set up in. But when we push one end, what's happening is we're pushing the atoms at one end. They have to push the next set of atoms. They push the next set of atoms. They push the next set of atoms. And actually, it isn't the case that the pushing that we do here immediately gets to the other end. Instead, what's happening is that we are compressing this end of our pole, and we have this little region of compression, and the atoms at this end, they're pushing on the next set of atoms, they're pushing on the next set of atoms, and they're pushing this region of compression down the pole. So actually, we already know of something similar that happens when we're talking in the air. What we're doing is our vocal tract is moving, and that's pushing the air, and we push the air, and as we push the air, we are producing waves of compression in the air, and those waves of compression move at the speed of sound in air, about 600 miles an hour. They'll move, but it doesn't happen instantaneously. The molecules of air that we pushed on with our throat, so to speak, they will push on other molecules, they will push on other molecules, and that process of moving that information from one set of molecules to the next occurs at the speed of sound, which is about 600 miles an hour, 700 miles an hour. The 330 meters per second is a more accurate value for the speed of sound at standard temperature and pressure. It depends on the pressure of the air and so on. Okay, so that's what happens in a gas and air. If you have a solid object, piece of steel or something, and you push on one end of that piece of steel, Exact same thing happens. You produce a region of compression, and that region of compression gradually moves down the steel pole at a certain speed. It moves down that steel pole actually at the speed of sound in steel. So because sound, normally it's carried by the air, but you can also conduct sound through something like steel. You're compressing one end of the steel and you're getting that compression is gradually moving down the piece of steel. So for example, when you, if you're, I don't know, if you have a, let's say you have a metal pipe and you bang on one piece of the metal pipe and somebody hears you a different piece of the metal pipe, that's sound that is being conducted through the metal pipe, not through the air. Okay, so the question is, how fast does sound go in a metal pipe? Or how fast does sound go in a piece of steel as opposed to in the air? And I'm not remembering precisely, but it goes at a few thousand miles an hour. And I don't remember exactly how many. And it depends on some details of the material. But just as in air, sound goes at maybe 650 miles an hour, in something like a steel bar, let's say it goes at 2,500 miles an hour. I'm not sure if that's exactly right, and it will depend on details. But so it's still the case that just like sound travels at a certain speed, the effect of this compression will travel at a certain speed in this material. So let's say we have this steel pole and it's 4 light years long and it's going all the way to Alpha Centauri, and we tap on one end of it, push one end of it. The problem is that the thing isn't completely rigid. It'll have this wave of compression that goes and it keeps going and it keeps going. And it'll probably actually in practice die out, but assuming it didn't die out, it will keep going, keep going, keep going. Eventually it will get to Alpha Centauri, but it would take a really long time. So if we sent a photon of light, then it would go at the speed of light. If we send this essentially sound wave in our pole, it will go at the speed of sound in that pole. And the question of how big is that speed of sound compared to the speed of light? Well, the speed of sound is always less than the speed of light in any material that we know right now. As the material gets more rigid, the speed of light gets closer to the speed of sound gets closer to the speed of light. So in air, which is not rigid at all, the speed of sound is comparatively slow. As we go to more and more rigid materials, stronger and stronger metals and things like that, the speed of sound will go up to thousands, 5,000 miles an hour, that type of thing. Still tiny compared to the speed of light. But if we imagine a material, which we certainly can't make, that would be incredibly, incredibly rigid, eventually we will get up to speeds that are close to the speed of light. In terms of how fast sound can propagate, but never as fast as the speed of light. So you'll never win relative to just sending a photon or sending a radio signal. You'll never be able to get something to go faster than that in a solid material object. But that's kind of how that works. Oh boy, there's a question here from Julian A. Who do I think the smartest person to ever live was or is or something? That's a weird question. Smartness is not one of these things that is on a scale of, person A is smarter than person B is smarter than person C and so on. If you try to assess how people will do in different situations, like, will this person be able to solve this problem? How long will it take them to do it? Depends on the problem, depends on the person, depends on, whether they are in an energetic mood right then, depends on lots of kinds of things. It's not something that is, and there might be some, I don't know, take a person like me, there's some kinds of problems I'm pretty good at solving. There's other kinds of problems that you might think, well, if this guy is at all smart, he should be able to solve this problem. And I'm like useless at solving these things. It's a thing where, different people, different times, different knowledge, but people have, they're able to solve different problems. Now, I think that, and sometimes by practicing a lot, you can get faster at solving some particular kind of problem, or better at solving some particular kind of problem. Like I spend a lot of my life trying to solve fairly difficult problems. I've learned over the years how to solve difficult problems. if I were instead spending my time solving a large number of very simple problems, I would probably have a bunch of different strategies. And I might be faster at solving the simple problems if I'd done lots of those, as opposed to being able to solve some of the more difficult problems because I've done lots of those. So I think it's a very, it's something where there isn't really a linear scale. Now people back in, particularly in the 1930s, people were very keen to have sort of a linear scale of intelligence, some kind of intelligence quotient, IQ or something, where you could just put people on a scale and say, this person is IQ smarter than this person and so on. And that was useful because people were trying to figure out, oh, I don't know, for people joining the army or something like that, you know, who would get this kind of job, who would get that kind of job. Some kinds of jobs require more analytical skills, less analytical skills. Some kind of jobs require you to be strong, physically stronger, these kinds of things. You know, can you rank people according to, I mean, physical strength? Okay, it's probably fairly easy at some level. You know, how fast you can run, something like this. You know, how accurately you can, you know, aim something or whatever. And then there's, well, how fast can you like figure stuff out? And what can you figure out? So people tried to invent these tests for, you know, how smart are you? And they tried to make these kind of puzzles of, you know, what's the next thing in the sequence that goes this to this to this to this to this. Problem is, pretty much any of those things, if you've done a lot of that particular kind of thing, you're better at doing that particular kind of thing. Insofar as people have tests where nobody has seen those tests before, then that's slightly better, but it still just depends on what other things you've done that are sort of related to that. I mean, like, for example, right now, you know, I'm watching the somewhat horrifying story of people trying to model this pandemic. And I'm watching sort of what happens when people make these different kinds of models and they get confused and they can come to some conclusion and so on. You know, I happen to have done a lot of kind of computational or mathematical modeling in my life. And so certain kinds of things are like, well, it's really pretty obvious that this is true or that's true, but it won't be obvious to other people. But it's not, I think, because I'm any smarter. It's just because I've done a lot more of this kind of thing. And so the intuition that I have about how things work is better developed, and it's faster for me to come to that conclusion or another. But, you know, it became the case that people have tried for a long time to invent tests that are kind of neutral tests, that are just tests of something intrinsic that one can call sort of smartness. And back in the 1930s, people came up with this idea, the general intelligence quotient. I think they used to call it G, the coefficient of general intelligence. I don't know what on earth this means. I think it's quite meaningless, actually. And in fact, you find that, and people, you know, when people make standardized tests, like, I don't know, SATs and things like this, there's a question of what on earth are they actually measuring? And, you know, really what matters in the end is, what do you want to get out of the answer to what are you measuring? So, for example, for the SAT test for colleges in the US, although many of them are now dropping it, probably a good thing, but it was, you know, what does it really want to measure? It might want to measure something like, are people going to do okay in their first year of college at this particular college if they get such and such a score in the SAT? That's a reasonable question to ask. And you can say, well, what's a way that you can probe the answer to that question? Oh, you ask these kinds of, you have this kind of quiz, but it isn't the case that if you do this kind of quiz and you do better on it, that you're intrinsically more intelligent. It's just you fit this particular mold that will cause you to have this effect in this particular case. So, you know, it's a, I mean, I've had the good fortune to know a lot of people who, you know, the test for me is if I talk to them about something and they kind of get what I'm talking about and they kind of jump ahead and they can say, what about this? What about that? It's like, oh, that person's really smart in my particular tiny little corner of the things that I'm interested in. You know, there are plenty of situations. It's always an interesting thing. You know, I have spent some of my life doing basic science, some of my life doing things like running companies and so on. There's sort of very different kinds of intelligence where sometimes it'll be really obvious to somebody how this or that business situation will work out, and that person, or how this or that situation with people will work out, and it's completely unobvious. If you ask that person something about some sort of mathematical kind of thing, they won't have any idea. but they'll have very good idea and be able to be very smart at figuring out something about how people will behave in some situation or some such other thing. So it's a very, it's a very multifaceted thing. And for me, there are people who seem smarter to me just because they fit in better with the way that I think about things and so on. And I think it's that way sort of intrinsically for everybody. And I think it's hard to make a sort of generalized, that there isn't really I don't really believe in this notion of a generalized concept of that. Okay, a question here from Saul. Do I think it is possible to make secret some big discovery related to, let's say, AI made by the government, similar to the way that the Manhattan Project was kept secret? That's an interesting question. I mean, it's more a question about the real world than it is a question about science, but let me try and address it. So first thing, a little bit of history. So the Manhattan Project, done in World War II, was the project to build the first nuclear weapons, the first atomic bombs. And the knowledge of how to make an atomic bomb was and has been largely kept secret. It isn't really that secret. It's just that you need an awful lot of pieces of technology to build an atomic bomb. And so the fact that, fortunately, there aren't more atomic bombs in the world is more a consequence of the fact that the sort of supply chain for the kind of uranium and plutonium, whatever it is, and all the different pieces, that those are not readily available. It's also partly it's a question of how you do all the engineering to build all the things you need to produce the right explosions inside the thing, to compress things in the right way, et cetera, et cetera, et cetera. It's kind of complicated, and you need a lot of engineering backup to be able to do it. So that's one case of a place where something has been both, it's fairly secret how to make it work, but it's also more to the point, the supply chain of all the pieces you need and the engineering that you need to be able to do, those are not readily available. And that's really more the way that can be sort of held back. Now, another example is cryptography, making secret messages. So that's a place where it used to be true that people said, you got to keep secret the way you're making the secret messages, because as soon as people know how you're making the secret messages, they'll be able to break the codes. But when you make a secret message, there's both the method of making it and there's the particular password that you use to make that particular message. And what was realized in the 1980s was that it actually was okay to tell people what method you used to make the secret message. You just had to not tell them the password. So it was a thing where for a while, people were saying, oh my gosh, we've got these methods for making secret codes and we don't want anybody else to know about them because otherwise they might be able to break our codes. Now, actually, the concern was not so much that. The concern was a different concern. The concern was if they get these ways of making better secret codes, then we won't be able to break the codes that they're using. So, country A says, we've invented this way of making secret codes. We don't want to give that way of making secret codes to country B because right now we're listening to all those radio transmissions made by country B and we're able to decode those transmissions because they're using inferior codes that we know how to break. So it was a big issue in the 1980s about whether one should tell the world how better secret codes work. And that was sort of decided kind of by default by people just publishing out into the open literature the ways to make these very secret codes. And I think that was I think it was sort of an inevitable thing that was going to happen, because unlike the nuclear weapons case, where there's a giant complicated supply chain, once you know the algorithm for making one of these secret codes, anybody can implement it on any computer. So, I think the real question of what you can keep secret and what you cannot is partly a question of what does the supply chain to the thing look like? Like, let's say you got this amazing AI and it had some method, but in order to train the AI, you had to use 1 trillion hours of, even that's not possible, we couldn't get to that, but even a few million hours of CPU time, of computer time, to be able to do the training. Well, in a sense, even the method by which the AI worked, you could tell everybody that. It's just they don't have the money to spend millions of hours of computer time to train the thing. Well, now it gets a little complicated because usually there are some entities in the world that would have the money to do that. Large governments would have the money to do that, but your average kind of private person would not. And so, I think that the reality of what can be kept secret is partly what do you need a complex supply chain or something that's expensive to produce to be able to replicate, and what's not. When it's just a fact, I think it's you can argue the whether it's good or bad to keep it secret. I think that's a complicated question. I think it's a very complicated question that's sort of more a question of geopolitics than it is a question of anything to do with science or technology. I mean, certainly the history of things has generally been, the world does better when things aren't secret. I mean, like a famous example, back in the, what period of time? Up until, oh boy, maybe the early days of universities, after 1200 AD, but before, let's say, 1800 AD. In Great Britain, the following thing was true. In England, it was illegal to do human dissection. It was viewed as being a sort of sacrilegious kind of thing to take, to dissect human bodies. And that caused trouble for medical research, because if you don't know how human bodies are built inside, it's tough to know how they work. And at that period of time in Scotland, it was not illegal to do these things. And so a lot of development got done in Scotland of those things that didn't happen in England. And, it's a very complicated thing, because there are other things where people okay, let's be very practical. Should one be doing, gain of function mutation research on viruses? Interesting question. Should we be making viruses that are more potent, more powerful than any that have existed in nature? Is that a good idea or not? Should the knowledge about how to do that, how widely should the knowledge about how to do that be spread? Well, the truth is that cat is already out of the bag, because like cryptography, genome sequences are, once you have the sequence, you have the story. Now, it may be complicated to be able, if it's a complicated thing to synthesize, there may be some sort of supply chain complexity there. But generally, it's one of these things where once you know that that's worth doing, you can readily do it. So I think that's another interesting case. Is if somebody discovers the absolutely magic killer virus that would just kill everything, so to speak, what to do with that? The fact is, I think for both theoretical and practical biology reasons, probably no such virus exists, fortunately. But that would be a good, interesting case in point of, can one keep it secret? Is there a sort of supply chain that's complicated enough to do that? I think that's an interesting question. And I think that, different governments around the world have different attitudes towards the notion of secrecy and what the obligations of people are to keep secrets if they know them, and all those kinds of things. And again, it's more a story of geopolitics. And I don't think there's any, it's generally one of these things where there's no right answer, so to speak. It's just like, well, I feel it should work this way, but somebody else may feel it should work that way. And kind of, the reason it's probably not a bad thing that there are multiple countries in the world is different groups of people have different general feelings about how things should work. And so, that's a good reason to have different countries and so on. Okay, that's enough geopolitics here. Let's see. All right, a few other things here. Parmenides is asking, any stories about Roger Penrose? So I consider Roger Penrose a friend, and I was happy that he won the Nobel Prize for Physics a couple of days ago now. Always a good thing. I'm a little amused by that because I view Roger as being much more of a mathematician than a physicist. I think sometimes I remember back in 1977 when I was a student at Oxford University, I wasn't very good at going to courses, but I went to one class that Roger Penrose gave about general relativity, about the mathematical theory of gravity. And the thing that was always charming about it was he would do these giant derivations on the blackboard, and he would go from one end of a big blackboard to the other end of the big blackboard. And at the end of it, he would very charmingly look up and look very, very puzzled because he'd got the wrong answer. And in a sense, that was probably a very educational thing, because I used to, have a great time figuring out what went wrong, where, and so on. And it was probably more educational than just sort of seeing, oh, there's this derivation of how this works. Actually, I just recently found my notes from that class. It's kind of interesting the way that the things that I learned about general relativity have become clarified, at least to me, in this project about fundamental physics that we've been doing recently. But I would say that I think Roger's contributions to mathematics have been, and sort of the very mathematical end of physics have been quite have been wonderful. I think his sort of thinking about sort of the physics of how brains work and so on, I'm less convinced by. I mean, one of his most important results, Hawking-Penrose singularity theorems, that basically say, under certain circumstances, it's inevitable that you will get a black hole. When you have certain kinds of sort of when certain things are true about matter in the universe, it is inevitable the black hole will form. And that means, for example, that the kind of giant garbage can at the center of our galaxy, the 100,000 solar mass black hole at the center of our galaxy that's gradually sort of, slowly accumulating lots of stars from our galaxy, there's sort of an inevitability of the formation of that's implied by Roger's singularity theorem. But two other big contributions that Roger's made. One is a thing called spin networks, the other is a thing called twistor theory. Both of them haven't really yet been fully explored. I think spin networks are somewhat like the models that we now have of space-time. They're a way of thinking about space as a discrete kind of thing, but his particular way of thinking about space as discrete is much more elaborate than mine, and it might eventually be equivalent, but I think it's overly elaborate. The idea of twistor theory, but a little bit hard to explain here, but it's a pretty mathematical thing, but it's looking like some of the things that we figured out about the sort of fundamental structure of physics need twistor theory. They kind of engage with that sort of direction in mathematics, which is really nice to see. Let's see. Okay, people are asking to see my particle detector. Yeah, I mean, we should do that at some point. I don't have it on the computer that I'm streaming from right now. And I need to try it because I was very excited because somebody sent this to me. It's a little, okay, tell you a little bit of a story. So how do you detect particles? You just got this one particle, it's going really fast. I told you one way using Cherenkov radiation. The main way that you detect a particle is that it, well, okay. The most common way is that it produces some kind of electrical breakdown in something. So let's give an example of this. So for example, when you have a lightning strike, what's happened is that there's this giant voltage between the cloud and the ground. And it would really like to be the case that electricity that's at this very high voltage would really like to be conducted from the cloud down to the ground. Really like there to be a wire from the cloud to the ground, but there isn't a wire from the cloud to the ground. But that lightning strike is temporarily making something like a wire. It's ionizing the air so that the electrons in the air are stripped away from their atoms, and the electrons, just like electrons can move in a wire, in like a copper wire or something, they can also move when they're stripped away in a plasma. they can move, and that's what's happening in a lightning strike, is that you're stripping the electrons so that they can move freely, so that the electricity from the cloud can be conducted down to the ground. Okay, so what happens is that if you have what's usually called an ionizing particle, if you have a high energy particle that might be from a cosmic ray, might be from something else, it is doing something a bit like that lightning strike. It's able to, in fact, it could even be that lightning strikes are initiated by the presence of, where the lightning strike happens could have something to do with, oh, this cosmic ray happened to come through in this place. And so that kind of created almost sort of a crack that then this giant, this column of ionization can be produced in. Okay, so the way people detected particles, ionizing particles, yeah, let's see, boy. Okay, roughly, what happens is you've got this particle, maybe it's a proton or something, and it's going to be, it has enough energy that it's going to be doing like what the lightning strike does, and it's going to be ripping electrons out of their atoms. And you can detect that happening by having a little sort of microscopic lightning strike. So an early kind of particle detector with this thing called the Geiger counter. And if you've seen, probably by now, I've got a Geiger counter somewhere, I could show you guys someday. Geiger counters in sort of the old time movies and things, you'll hear them, it'll go, click, 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 click. And then when you're near a piece of a source of radioactivity, a source of particles, it'll go click, 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 click really fast. And that's every one of those clicks is like a microscopic lightning strike that's being initiated by one particle going through this this kind of voltage difference and a gas, this voltage difference in a gas, and sort of that the presence of that particle causes it to break down to have this little microscopic lightning strike. Okay, so that was an early method for detecting particles. So years ago, I said to people who detected particles, these memory chips that exist in computers, they're very sensitive to, to sort of being perturbed electrically. And, in a typical modern memory chip, it's maybe, I don't know, 10,000 electrons represent one bit of information. And so if you kind of kick those and you have an ionizing particle that goes near there and it strips electrons out of atoms and things like this, then you're going to, every so often, you're going to change one of those bits. And that might be a way to detect particles. They were like, no, never going to work. Okay, whatever. So many, many years go by. And in fact, the method of using things like memory chips to detect particles has now become quite standard. And the idea is, you've got this memory chip, it's got 1 billion bits of memory in it. And every so often, if a particle goes through, it's going to ionize some atoms and it's going to produce some electricity there. And that's going to show up as being a bit got flipped in the memory chip. And you can set up memory chips so that they are, usually you want them not to be flipped. So you want to sort of hold them back from that, but you can set them up to be sort of closer to the edge. So they're have a higher tendency to be flipped. Back in the day, 1970s, 1980s, used to be a problem that semiconductor memory, memory chips and so on, used to have a problem with cosmic rays quite often. And for example, so the Earth's atmosphere shields us from most cosmic rays, but the higher you go, as you go up, like to Denver, for example, which is a mile high roughly, the amount of atmosphere above you is less. And so there's less shielding of cosmic rays. So there are more cosmic rays, more radiation in Denver than there is on the surface. There's also more radiation near the magnetic poles of the Earth because of the way particles spiral in through the magnetic field of the Earth, more close to the poles. In any case, so there are places where there's more cosmic rays. And it used to be the case that computers would have more memory errors in when you had them in these places where you were higher up in the Earth's atmosphere with less shielding from cosmic rays. And that is a big problem in spacecraft where you don't get much shielding at all. And that's a big problem that you can have problems from cosmic rays and so on. More of a problem when you get out of low Earth orbit, you go into deep space, you no longer have the magnetosphere of the Earth, which can protect, can deflect some of those particles away. But in any case, that sort of got solved because memory chips on at least server type computers tend to have error correction, which means even if one little bit is flipped, there's an algorithm that can say, no, we can tell that one bit got flipped, that bit is wrong, let's correct it in this way. That kind of error correction doesn't exist on things like phones. The memory in phones doesn't tend to have that. So in fact, people have tried this project recently to make a giant global cosmic ray detector by having people just essentially, well, they're not just using memory chips, they're also using the cameras of phones, which use the same kind of electronic mechanisms. And they're saying, just cover your camera, no light gets to the camera, but just if one of these charged particles goes through the camera, it will essentially register a pixel. See if you can detect cosmic rays that way, and see if maybe you can detect sort of giant cosmic ray showers spread across lots of large area on the Earth by doing that. It's kind of a fun thing to try to do. I'm not sure it's yet been very successful. But why was I digressing on this? We were talking about, yes. So anyway, this idea of using kind of memory chips or things like the way solid state cameras work to detect particles is something that's become pretty common. And there's now a little detector that somebody sent me that you can connect to a computer that actually can show you the track of a particle going through. And so I haven't seen one of these yet. I haven't really hooked it up properly. I really want to see a muon track because I've never really seen a muon, and I want to do that. Let's see. Yeah, there's people asking for me to show various kinds of objects I have. That'll be a fun thing to do. All right, one last question here from Krasner. Do I believe that there was an idea of technology before modern civilizations? So that's one of the questions there is there technology that was understood but has been lost? Quite possibly, yes. I mean, we know one really good example of that, which is mechanical computers. So there is this thing that people used to think, oh, even mechanical computers, even computers that have cogs and things in them, were not invented until the 1600s. That's what people thought until very recently. And then it was discovered, somebody found, well, it's a sort of funny story. There's an island called Antikythera, it's a Greek island, and there were some sponge divers off the coast of Antikythera around 1900 who found this shipwreck. And they found all kinds of cool things in this shipwreck, all kinds of statues, all kinds of other stuff. And they brought all this stuff and it wound up in the Athens Museum. And one of the things they found was this kind of lump of stuff, kind of a lump that was, kind of a sort of corroded metal lump. Okay, so it goes. Okay, sometime I think in the 1950s, somebody by mistake dropped this metal lump on the floor. It broke in two, and at the exposed surface, there were some cogs. So that's a really bizarre thing because people didn't really know that things with cogs had existed like that, precision things with cogs that existed. Well, for a long time, people didn't really know what this thing was. Eventually, it became possible to do CT scans so that you could sort of see inside without taking the thing apart. And then actually a friend of mine funded the project to really try and decode how the thing worked. And basically what happens, it's not known exactly when it's from. It's either around the 1st century BC to the 1st century AD. It's a thing which is a mechanical calculator. It's got many, many cogs, and it computes the position of the sun and the moon and the earth, and it has a sort of elementary way of computing the position, the times of eclipses. It has all kinds of stuff in it. And it also has as kind of a clue, it has marked off in time the time of some version of the Olympic Games back from those days. And so that gives kind of a clue about where it came from. It probably came from the island of Sicily, particularly the city of Syracuse in Sicily. That was where a chap called Archimedes, who was a well-known mathematician of antiquity, lived. And it's always been kind of my little sort of concept that that Archimedes, as well as coming up with all kinds of modern things that we know in mathematics today, also had a business kind of making mechanical computers on the side. It's kind of funny for somebody like me, because I've spent my life making tools that are software tools now that allow one to do things like mathematical computation. And it's kind of nice to imagine that maybe Archimedes was kind of in the same business that I'm in. But in any case, that was a case where nobody had any idea that there were mechanical computers in antiquity. They thought they originated in the 1600s. But by a chance discovery, there's only one of it, there's only one example. We know that these things existed then. We don't know how many things like the Antikythera device existed. Now, there were some clues, like Cicero, ancient Roman orator, writer. He mentioned that he had seen some kind of calculational device, but nobody took that seriously. They didn't know what it meant. So it's like, we don't know what that is. So nobody really paid much attention to that for 2,000 years. So I think that so that's an example of where something, technology for antiquity sort of showed up again. And there's some other ones which are a little bit mysterious, to do with materials like various metals and so on that existed in antiquity. I mean, there's some really weird things, like there's some metals that couldn't have existed at that time in antiquity because people didn't know how to make them, but actually they probably came from meteorites, which were obviously rare, but you could find them, and then they have metal in them, which was of a kind that couldn't be made by the technological processes of that time. But there's a question of what other technology from ancient times could have been lost today. There's possibility of various kinds of medical things. I mean, there's a lot of drugs that we have today. I mean, there aren't that many known drugs. There's maybe less than 2,000 sort of known, approved drugs. And many of them quite a lot of them are derived from natural things, so to speak. From some particular bark of some particular tree has some particular molecule in it that turns out to be useful for some particular purpose, and so on. And it's quite possible that, in antiquity, there were other things known that, oh, by the way, if somebody develops purple spots of this kind, you use the bark of the such and such tree and it fixes it. Exactly how that works and what diseases people might have had then versus now, it'll be different. And, there was no FDA to approve things, and maybe some of it was complete nonsense, but that's an example of something that quite possibly could have existed. Could there have been other technology that we don't know about today? An interesting question. I mean, the Antikythera device is definitely a wake-up call about that, because it's like there's lots of kinds of things. So for example, anything made of wood, it's going to be gone. We don't know what it is. The very first mechanical calculator probably was made by a guy called Chicard, who was a friend of Kepler's. The thing he made was made of wood. And so that hasn't survived. The first metal calculators, like the one made by Pascal in 1640s, has survived because it was made of metal, and it doesn't sort of just sort of decay away. So it's hard to know what could have existed in those at that time. And is it quite a lot of technology we have today sort of builds on top of, well, there's two kinds of building. One is conceptual building. The other is just manufacturing of devices. So I don't think that there was a webcam that existed in antiquity, because to get to a webcam, you have to have an awful lot of stuff that has to exist in the kind of supply chain of you have to have that supply chain to be able to produce that kind of material. It's an interesting question. What other technology might have existed that we don't know today? I don't know. I mean, there are who knows? Maybe there are throwing sticks, like boomerang-like things that somebody had figured out this really clever way of shaping it so that it would do some really clever thing that we don't know about today because it was made of wood and it's just been lost. I think a comment from Merrick here. There were papers found from Alexandria that detailed steam engines. So that's another interesting point. So Hero of Alexandria, for example, was famous for having sort of invented a variety of kinds of things. Yes, it is one of the issues that things sometimes get invented for toys and nobody knows what the point is. So there were many kind of automata toys that are like little robots that do things. And it's like, okay, that's cool. You know, that existed in 1500, 1600 AD. And it's like, that's cool, but what do we do with it? Oh, you make an industrial robot out of it. What's an industrial robot? We haven't thought of industrial robots. So yes, there are things that are viewed as being sort of toys and novelties that end up being things that are important later because people get the sort of, you know, there's the advance of the concepts and the advance of the supply chain of the technology. And, you know, it can often be the case that there are things where people say, I mean, people had known about, oh, I don't know, well, magnets, they kind of figured out, I think they knew about magnets, I think a solid 1,000 years before people started using them. I'm not sure about this. I'm not sure when compasses were invented. That's a good question. But certainly, I don't know, things like liquid crystals. The substances that make liquid crystals were known for a long time, but the idea of using them to make displays, that was a very recent idea. So yes, there are plenty of things. I mean, another famous example, well, here's an example. So, you know, carbon comes in several forms. It comes in graphite that you have in pencils. It comes in diamond. All of those are just carbon atoms. They're just arranged in different patterns. And people thought, okay, there are two forms of carbon. Great, all done. Well, it turns out that in common soot, there's actually another form of carbon called, usually called Buckminster fullerene, after Buckminster Fuller, who described not about carbon, but described this kind of shape that's kind of the pattern of seams on a soccer ball. You can make that into kind of a network, and you can imagine putting carbon atoms at the sort of positions in the soccer balls. And I think that the thing that was realized is actually common soot has, if you analyze it correctly, has tons of these buckyballs. And these buckyballs, well, that turned into things like graphene and other kinds of nanomaterials, which one is slowly managing to realize have all kinds of uses. But yes, it's often a challenge once something is known in the world to know how it will be used. Steve is pointing out that there were vacuum tubes for 100 years before ENIAC. Is that right? I don't think quite that long. Vacuum tubes, the thermionic effect was around 1910, I think. So I think that I'm guessing there were only vacuum tubes for 35 years before the first computers made of vacuum tubes, I think, because the first radios with vacuum tubes were, am I right? In the 1920s, there were certainly radios with vacuum tubes. And for those who don't know what vacuum tubes are, oh gosh, another time, maybe another time. They're the technology that predated the transistors that are made for all of our current technology. And instead of transistors, which are these microscopic things made out of solid pieces of semiconductor, vacuum tubes were these glass things that had actual glowing filaments inside them. And when I was a kid, for example, it was still the case that transistors were rare and vacuum tubes were pretty common in devices. Okay, here's another comment from Merrick about batteries. I don't know about batteries. I'm a little suspicious about batteries because developing the electrochemistry to develop a potential in an electric potential in a battery is not so hard and can happen even, quotes, naturally. It does happen naturally. It happens in our nerve cells and things like this. So knowing, I mean, that's another complete can of worms in understanding ancient technology. Is you find something and then you say, what was it for? You find the Stonehenge arrangement of stones. What was it for? Was it some amazing piece of technology? Like I just saw a couple of days ago, somebody who says they've discovered that there was amazing acoustics, amazing sound properties of Stonehenge. It's like, really? Well, was that intentional? Was that part of the design of Stonehenge? Or is that purely coincidental? And it's, people often wonder, oh, they found, this arrangement of stones left in, this is a thing where I live in New England. It's a common issue. People will find things that were an arrangement of stones. Was this an arrangement of stones put there by Native Americans, 500 years ago on purpose, or is this just a random collection of stones? If it's on purpose, what was the purpose? Describe what was actually going on. So it's often kind of hard to, when you find an object, knowing what it was for is non-trivial, and maybe that purpose doesn't exist anymore. I mean, people, I remember, it's a story I've kind of told a few times. I was notable incident for me of visiting some archaeological site in Peru where there are all these stones and they're all arranged in different ways and all kinds of things. And you ask kind of, what was that for? And the person who was showing us around was like, that was for ceremonial purposes, which is it translates into, we have no idea. We have no modern context for what this was for. It was for some, ancient, quotes, ritual. Well, maybe the ancient ritual, I mean, maybe, sitting here and waving hands and looking at a camera lens might be a modern ritual of some kind. What is it for, so to speak? It's one of these things where what is somebody's very purposeful activity is another person's ritual because they don't understand what it's for. And I think that's sort of an issue in trying to understand ancient technologies. You find a thing and you ask, what was this for? And it may not be, if we don't have a modern context, we don't have a similar thing that's happening today. It may be, we may not be able to connect those things. All right, I have to wrap up because I have to go do something else. But anyway, great to chat with you guys, and thank you for all these interesting questions and comments. And I look forward to seeing you next week. All right, I gotta go. Bye for now.